Hey kids, time for another log time. Just a little quick hypothetical for you. You're walking down the street and someone comes up to you and says, I'll give you $100 if you can tell me the log of 100. And you'd say, well, that's easy. It's 2 because 10 to the power of 2 is 100. They said, okay, that's pretty good. Here's $100. I'm going to give you another $100 if you could tell me a log of 50. Then you'd maybe furrow your brow a little bit. You'd be like, well, if I had my calculator, I could type in a log of 50 and I could push equals and tell you 10 to the power of 1.69 would be 50. Okay, sure. But what if they offered you $1,000,000 and you had to figure out log base, I don't know, something other than 10. Let's say log base 8 of 50. You could use your calculator. You go, okay, well, let me look for the log base 8 button. And you see, okay, well, here's log, here's ln. I see that 10 to the x is right there, and e to the x is right there. So even if you don't know what ln is, it's a pretty big clue that it's base e versus base 10 here. But how do you get base 8 or some other base? That's the question we're going to answer today. It's not a real hard thing, but I got to show you a little bit of math. Turns out that some of you might even have a calculator where you can enter in a base of something other than 10 or base e, but for a lot of us, even high-powered calculators like this TI-83, you can't actually do it. So you need some sort of method to figure it out, and that's what today's all about. So let's move this bad boy over here, and let's get on with the lesson. So our next section is 5.4. It's the change of base rule and a little bit on the natural logarithm. So basically what we're looking at here is how you can use a calculator and also just some other cool things you can do with this change of base rule. So one thing you must understand is the common logarithm button usually is log, and that's log base 10. And the natural logarithm button is ln, which is log base e. This I have mentioned a few times, but it's pronounced lawn, as in mow the lawn. I don't totally know why they call it that. It's ln, so I guess they said one, I don't know. Anyway, it's log base e. If it's a little small, there you go, so log base e. Okay, so those are your two buttons on most standard calculators. Now, if you want to evaluate a logarithm that's a base other than 10, you got to convert it into some form your calculator can understand. So the change of base rule is this. I'm just going to show it to you, and then we're going to prove it. You can rewrite a logarithm of some base that you don't like. So let's say it's log base b of x. You can actually write it as log base a of x over log base a of b. Don't worry about a right now. I will explain what a can be in just a sec, but right now what we can appreciate, hopefully, and there's these restrictions, and we'll talk about those in just a sec as well. The log of the x goes up top and the log of the b goes down to the bottom. So it's kind of this way of splitting the argument and the base. Argument goes up top, base goes on the bottom, like that. Now what this base a of the new logarithm is guess what? That gets to be anything you want. So you can choose it as long as it satisfies the restrictions. It is a base, so it has to be bigger than 0 and it cannot be equal to 1, just like the original base b. And we've been calling that base c sometimes. Doesn't really matter what letters you use. Now there's a little note here that says most of the time you would want to choose it to be 10. So that's just simply because calculators all have base 10 logarithms, but you can choose it to be anything you want, and that's the beauty of this. So if I wanted to calculate, what was the hypothetical question? Log base 8 of 50, I think it was. Then what we could do is we can rewrite that as log base 10 of 50 divided by log base 10 of 8. So you would actually just go to a calculator, you would go log of 50, and you would divide it by log of 8, and that should give you your answer. So the answer to the hypothetical question, what is log base 8 of 50, would be 1.88. And then, of course, that's the same thing as saying 8 to the power of, I think, 1.8812, blah, blah, blah. And hopefully people are kind of knowing by now you could actually use the answer button for that for an exact thing, but that's going to give you basically the answer. So that's basically 50. So only not 50 just because I rounded. Okay, so that's the change of base rule. With all things in the log unit, it's nice to see why it works. So let's have a little look at the proof here. So proof of the change of base rule. This is actually a really really easy one to prove. So you start by saying, okay, so we've got some quantity y is equal to log base b of x. Writing that in exponential form, you've got base b to the exponent y will equal x. So this is just rewriting in exponential form down here. Now, what you can do, and I think we've used this once before, we can log both sides. So logarithming, this is probably not a word, but it is an operation that you can do. My little Texas Instruments thing here is just blocking this. Here you can choose any base logarithm. So you can take any base log of both sides as long as you're doing the same thing to either side. That's a general thing in all of math. You can do it. So we're logging both sides. They do have to have the same base, but that's simply enough. Using the power law, we can take the y down in front to get y log ab equals log a of x, and then you can just do some division to move log base a of b down below, and you wind up getting this. So y equals this. And of course, y was this, and y was this, so therefore this thing and this thing are identical. Okay, so these are the same. Okay, so just like all proofs, hopefully that makes some sense. If it doesn't, well, you can always remember the result, but that's what it is. So it's a really handy rule. Okay, so example 1 says simplify then evaluate the following with logarithms. This one is super simple. This one you might make an argument that we're not simplifying, maybe we're expanding it. I don't know, I always have trouble with that word, but log 8 divided by log 3. Evaluating this, there's not really a way we can do this nicely, so we're actually going to go over to our calculator on the side. So, oh no, oh, there we go. Okay, let's clear. Okay, I think it likes it better when I use my mouse. So we're going to go log 8. I'm so happy that I figured out a way to make this not crash. It just stays on top, so now I can do this. Okay, so log 8 divided by log 3, or log base 3 of 8, will give us a value of 1.89 ... That's close enough. Just take a second, think about this. Does this answer sound reasonable? Remember, the base to the exponent should equal the argument here. So is 3 to the power of 1.89, does that sound like that could equal 8? I know 3 squared is 9, so 3 to the power of something a little less than 2 should be something a little less than 9. Okay, so the simplifying here looks like, in this case, we've got log base 7 of 2, and we've got log base 7 of 3. Is there something I can do here? Now, if you remember from very recently, we had a product law. So because these are sharing the same base and they're two logarithms added up, we can actually write this as log base 7 of 2 times 3. And then this becomes log base 7 of 6. And I could evaluate that as log 6 over log 7. So we just jump over here and real quick little calculation. Log 6 divided by log 7. And we get 0.92 equals 0.92 . Again, I don't really care about rounding. Cool beans. Okay, for C, this is one with some multiplying, and you know this all essentially turns into just a bunch of fraction multiplying, because when you see a log, you should actually just think it's a fraction. So log, now here's a thought. I'm doing log 8 over log 4. I could leave these as base 10, but I think I might choose this to be a better base. What do you think I should turn it into? What base should I use? What's that you say? I can hear you yelling all the way on your side of the internet. I should turn it into a base 2? That's a great idea. Doesn't super matter, but since everything here is a power of 2, this might actually make it a lot easier. So this becomes log base 2 of 8. I can actually turn this into 3, and then log base 2 of 4 is 2. And then let's see, log base 2 of 32, I believe that's 2 to the power of 5, so that's 5, and then this will be over 4. So this winds up being 15 over 8. Cool. So sometimes the change of base rule can be handy if you want to actually evaluate the logarithms. You don't always have to leave them as log form. If you can ever turn it into a number, you should. Okay, example 2 is a totally different style of question. This is actually going to go back to when we talked about different bases look like transformations. We're going to prove that now here. So how does the graph of y equals ln x compare to y equals log x? Let's sketch both on the same graph. So what I could do here is I could do a table of values and I could work these both out, but I'd actually like to think of this a little more in a transformation. So this here we can see is base 10. So if you're comfortable with logarithms, you know that some key points are, they all go through 1, 0, and then the next point here, unfortunately, it's going to be kind of off to the side, that's going to be 10, 1. And then we'll also have some other points here, but I'm not going to worry about those too darn much. I'm just going to use those, and then the log graph will look something like that. So that's y equals log x. If I wanted, I could table values and work out this other one, but I'm going to use something what I think is a little bit cooler. So we know this is y equals, it's identical to log base e of x, okay? Ln x is log base e of x. They are the same thing. They mean exactly the same thing. But using the change of base rule, I can actually do log x over log e. So one thing I can do here is I can now, I'm not going to do anything with log x because that's my variable, but log e actually has a value. I could go over to my calculator and I could go log, and then I just have to find e, there it is. It will be somewhere else on your calculator. But when you type that in, we get 0.434. So this would be the same as log x divided by 0.434. Or if I wanted to think of it maybe in terms of a multiplying thing, because I want to think in transformations, I could go 1 divided by the answer to get the reciprocal, and that's the same as about 2.30. So this is the same as 2.30 times log x. So what I can see here is that this number out in front, this is a vertical expansion, right? This is my function. That's my function, so any number multiplied by the function will vertically expand it by a factor of 2.3. So without having to do a table of values and all that, I can actually say the points I would have here would be 1, 0 is not changing, but 10, 1 is actually going to go up to 10, 2.3. 2.30 or whatever. So what I can see here is my graph is actually going to get, I guess, taller, and then it's going to go down a little faster. And that's what y equals ln x would actually wind up looking like. It looks a little bit higher than log x. And what we can see in general is by making the base smaller, we get a taller graph. And I believe way back when we were introducing it, we got something similar. Cool beans. Okay, jumping back to a more algebraic equation here. We can now simplify an expression with x's and all that. So this one, let's see, what would we first do? Now it's been a while since I've looked at this, so this is going to be fun as I awkwardly try and figure out how to evaluate this. So what I see is I've got 6 log base 9 of x minus 12 log base 27 of x. I'm subtracting 2 logarithms, so it might make sense for me if they were the same base, I could use that product rule. I cannot use that unless they're the same base, but what I'm going to do is I'm going to go 6 log x divided by log 9, and then I'm going to subtract from the 12 log x over log 27. What base do I want to use, though? I get to choose anything I want, and I could go with log base 10 of 9 and evaluate it, but those are going to be gross numbers. I can see that 9 and 27 are powers of 3, so you know what I'm going to do? I'm going to stick a 3 and a 3 and a 3 and a 3. And the big note, bases must match on the top and the bottom. The change of base rule allows you to change the base to whatever you want, but it's got to be the same. Okay, so when I do this, this is pretty helpful. This is going to be 6 log base 3 of x, and then what's on the bottom, log base 3 of 9. 3 squared is 9, so this is simply 2. And then this one here is going to be 3 cubed is 27. Wunderbar. I'm going to simplify. So the 6 and the 2 can cancel to get 3 and 1. The 12 and the 3 can cancel to get 4 and 1. So this is 3 log base 3 of x minus 4 log base 3 of x. And then finally I get negative log base 3 of x. I don't necessarily know if there's too much more I would want to do with that. There's a lot of properties of logarithms where you can fuss around with this. Like I could take that negative sign, I could bring it up into the exponent. So I could say this would be like log base 3 of x to the negative 1, which would be 1 over x. I could maybe even write this as negative log x divided by log 3, but I think this is maybe a little more work than I need to, so you know what, I'm not even going to worry about that. I'm going to say those are probably not necessary and just leave it right there. Those of you saying, couldn't you have done the quotient rule? And you absolutely could if you took that approach. And I'll just show you one other way, because I did say when you're subtracting logs, you might want to use a quotient rule. You could have also done it this way, where you use the quotient rule. What you would have had to do is you would have had to write it as log base 3. You can't have coefficients in front, so it would have been x cubed minus log base 3 x to the 4th. And then this would have turned into log base 3 of x cubed over x to the 4th. And you can actually see what that would have turned into is that actually would have turned into log base 3 of 1 over x. And that's precisely the same thing. So that's kind of a neat little thing you can do with logs. There's so many different ways you can express them. Okay, last question here. All right, so this is 1 over blah, blah, blah. You can read. I don't need to narrate that part for you. What I'm going to show you is what you can do here. So the first thing I see is I see the opportunity, yes, I said opportunity, to do the change of base rule. So what we wind up having here is we've got this situation. Now, this is gross, so remember 1 divided by a fraction means you can just take the bottom and flip it, so this turns into log base 2 over log base 10, and then this turns into log 5. I realize I just said base 10, I just meant log 10, and we get this. Now, it turns out that at any point, if you can evaluate the logs, you should. Log 10 is 1, and so is this one. So this actually becomes log 2 plus log 5. Now I have no idea what log 2 is or log 5, but if you notice these are both the same base logs. They both have no coefficients, so we'll use the product law. And we can make this equal to log of 2 times 5, which is log of 10, which is 1. Look how beautiful that is. Can you believe we started with this, discussing this, and we simplified it? So simple. Anyway, it all turned out to be equal to 1. Cool beans. Just stare at that for a sec. Isn't it beautiful? Amazing logs. Okay, last one. Example 4, use the change of base rule to show why the restriction on log base b of x is b is greater than 0, b cannot be equal to 1. So this is something we've been saying, and we've talked about this a little bit before in its relation to exponentials and how the base has to be positive because negative bases don't make a lot of sense. But we can do one more thing here. So another way of looking at this is log base b of x can be expressed as log x over log b. So why is it so important that b has to be greater than 0? Remember, you can't take the log of a negative number. It doesn't work. If you don't believe me, go to your calculator, type in log. Hello, calculator, you fell asleep. Can't believe they programmed the falling asleep battery saving function on the virtual calculator. Anyway, so log of -1 doesn't work, right? You always get a non-real answer. So you can't take the log of a negative number. therefore we would say b must be bigger than 0. Okay, this is not a complicated question, but it's another way we can look at why these restrictions exist. If you don't really understand fully the argument that an exponential function has to have a positive base, you can also say that you cannot have log base, log of b on the bottom, because you can't take a log of a negative number. Now, why does this one exist, though? Why can't b equal to 1? You can also say, since log 1 equals 0, right? That's a general fact about logs. You also can't have b equal to 0, since you'd be dividing by 0. So if b was 1, log of 1 is 0, and the denominator, there's the word I'm looking for, the denominator would be equal to 0, and you'd be divided by 0, and you'd also have that. So therefore, you'd also say b cannot be equal to 1. Cool. Okay. Anyway, that was just a fun little thing right there. I think that's about it. Now, this change of base rule can come in a lot of different forms. This can help us prove all sorts of stuff. But for now, that's enough. We'll see you on the next one.